Alright, hello everyone, I'm Stefanos. I'm a fourth-year PhD student at the University of Illinois at Urbana-Champaign. This is a re-recording of the presentation for DAS, the dynamic rewriter that was published in Sigma 2024. So along with the paper, I provided ACM with a recording. Now if we're honest about that, even though that recording was pretty cool because it was recorded in the conference hotel the night before the presentation, it's not that good. So, because DAS recently got an honorable mention for the Best Artifact Award at Sigmund, I thought of creating a higher quality version of that presentation. So here we go. The good thing with this recording is I don't have limitations that I had in the original. For example, a good thing about DAS is that you can run things on the fly. Like, you can just open up a notebook and do a live demonstration as part of the presentation. And I thought it would be really good to do that, but unfortunately, we were not allowed to do that. Because we could not go up there on stage with our laptops. Of course, I don't have this limitation here, so we're going to do that. Instead of showing you stuff, I'm going to be running stuff. So with that, let's get started. Alright, so here we are in the slides. So the paper is DAS, Dynamic Rewriting of Pandas Code. And I'm Stefanos. This is joint work with Daniel Kang and Charles Mendes. We're all from the University of Illinois at Urbana-Champaign. Exploratory Data Analysis, or EDA, is the process of exploring a dataset to find interesting characteristics. So this is where you have things like plotting, finding max, mins, deleting relevant data, things like that. Now, EDA creates an important class of workloads because thousands of EDA notebooks run every day on Kaggle, Google Colab, and on people's personal laptops. The main driving force behind EDA is Pandas. But the problem is that Pandas can be slow. And that's especially true if you make bad use of it. So here's a concrete example. So what I have here is a series of 10 million random numbers. And what I want to do is find the 5 smallest elements in this series. One way of doing that is to first sort the series and then take the first 5 elements. Another way of doing that is to use the Pandas provided and smallest function to find the 5 smallest elements directly. Now, according to the documentation, these two are equivalent, but as we will see, they have very different runtime performance. So the original one takes about a second, whereas the optimized one takes about 100 milliseconds, so we have about a 10x speedup. So the takeaway here is that depending on how you write your Pandas code, you may have significantly different performance. Now, there are many Pandas replacements that try to improve the performance of the Pandas API, tools like Modin, DAS, Qualas, and PolarS, but unfortunately, they don't help in EDA settings. And to show that, we perform some simple experiments. As testing code, we use some common EDA operations. We use a pretty powerful machine, and we use a 2 GB dataset that has been used in prior work. It's the NYC taxi dataset. All that is detailed in the paper. Here are the results. On the y-axis, we have the 3 EDA operations we test. On the x-axis, we have the 4 different Pandas replacements and Pandas as a baseline. And it's important here to note that every number we see on this table is a slowdown. So if we look at the whole table, we'll see that every Pandas replacement slows down every EDA operation. And slowdowns are not the only problem. For example, we have out-of-memory failures. Now, this is interesting because remember, we're using a 2 GB dataset on a machine that has 102 GB of RAM. And we can also have API compatibilities. This is basically when you use some part of the API that an alternative doesn't support. So now the question is, why do we see these problems? And we contend that it's because EDA presents some unique challenges. For example, EDA code is ad hoc, not idiomatic, and diverse because people are trying to get something working quickly. Here's an example from a real notebook that, as it says, does EDA. And here we have a for loop. We have a sequential for loop that accesses rows independently, which is generally something that is not very good for the Pandas API because it's better at working in bulk. But nevertheless, such code appears out there in the wild. So any Pandas implementation, Pandas API implementation, needs to deal with it gracefully. The other thing is that EDA runs on a single machine. In particular, it doesn't run on a cluster. This is generally okay if you're using Pandas, because Pandas itself is single-threaded and it can't make use of distributed storage or things like that. It doesn't even make use of the disk. But it is important to remember that if you're running on a different machine, you have different requirements than if you're creating an implementation that is supposed to run on clusters. Now let's compare and contrast these challenges with the use cases of these Pandas replacements. All of these replacements basically perform bulk parallel optimizations, and these work well on idiomatic Pandas code, especially if you're staying within the Pandas API. And they work very well on clusters because they try to parallelize the Pandas API, all of them in different ways. For example, Modin uses Ray underneath, Dusk has its own engine, Koalas uses Spark, PolarS has its own implementation of multi-threading. But all of them, they try to parallelize the Pandas API, and so they work very well on clusters. But as you can see, these are almost exactly opposite from the characteristics of EDA, and that explains the kinds of failures we see. In particular, these optimizations are prohibitively expensive for EDA. So here we set some design goals for a method that is going to be able to optimize EDA workloads. The first design goal is that it should be a lightweight solution. That means it should have minimal slowdowns and near zero overhead. Second, it should be automatic and correct. Generally, that means you should just be able to import it and be done with it. Shouldn't have to change your code. And the third one is it should be effective. So it should not only not slow down your code, but it should also offer significant speedups. We propose DAS, a dynamic rewriter that achieves all of these design goals. So let's come back to the example we saw earlier. And what I'm going to do now is I'm going to delete the optimized version. I'm just going to leave the original version there. And I'm going to simply import DAS. So now I rerun my code. And we can see now that the original version runs in about 83.8 milliseconds, which is even faster than the optimized version we saw before, and of course faster than the original version, which is to say that Pandas has near zero overhead. Now you might say, Stefane, this is great, but this is also kind of fabricated. I mean, you have 10 million random numbers, and the speedup is also not great. It's only 10x. Luckily, I've got you covered. So what I have here is an example taken from this notebook here. If I remember correctly, it's from a book on movie recommender systems. And this notebook has a bunch of upvotes and copy and edits. So apparently people have found it useful. And if I go back here, so what I do is just I import the data set and I replicate it a little bit to see clear effects. And there's this weighted rating function that does a bunch of things that are important to movie ratings, I guess. And it has all the nice stuff, right? It has array accesses, computations, access to global variables, I mean, a bunch of complicated stuff. So what I do here is I just apply this function over the whole data frame. Now, let me run this code to see how long it takes. But unfortunately, it's going to take quite a while. So cut until it's done. All right, so we're back here, and it took about 13.5 seconds. So now what I'm going to do is I'm not going to change anything in my code, except I'm just going to import DAS. So I rerun the code from the beginning, and now we can see it takes 26.4 milliseconds, which, with the help of Google, is about a 511 speedup, which I think is quite significant. So back here at my trusty slides, I have the DAS design goals again, and I would say that with these examples, we have achieved the goals. So we have a lightweight solution, it's near zero overhead, it is automatic and correct, we don't have to do anything except import it, and it just preserves the correctness of the code. And it's also effective, so it can give significant speedups. Now, the main question is, how does DAS do that? Our main insight is that we identified program rewriting as a technique that meets all of these goals. So here an overview of how DAS works under the hood. Everything starts with a Jupyter cell that someone wants to execute, presumably by pressing Ctrl-Enter. And then what happens is automatically this cell goes through the DAS system. First, it goes through a pattern matcher that identifies suboptimal patterns. For example, it sees that sortValues.head is suboptimal. And then these suboptimal patterns go through a rewriter that rewrites them to a faster version. And eventually, the resulting code gets executed. And all that happens behind the scenes. So the user doesn't have to do anything. Now, the way DAS does that is by implementing a set of rewrite rules. these rewrite rules have the form LHS to RHS. And the meaning here is if Dias encounters the LHS, then it replaces it with the RHS. Here's an example of a rewrite rule that we call sortHead that handles the case of sort values followed by head. The way this rule works is that it has some what we call varying parts, or you can think of them as generic parts, and some concrete parts. So basically this rule defines a template that can match through the varying parts many different kinds of concrete instances. So here, this rule uses this special at curly brackets notation to denote a varying part. And we say if we have any expression, so here goes some AST, Python AST rule to say what we're trying to match here. So if we see any expression, if we see such an expression, we give it a name. We'll see in a little while why. But if you see an expression followed by .sortValues followed by head, we then equal to a constant integer. So that's what this says here. Then you should replace it with this. So first of all, we see that through these varying parts, this rule is going to match many different concrete instances. All these instances should have, for example, sort values verbatim, because that's not a varying part. It's just constant. But for example, it can match different kinds of expressions. So you can match with this rule df.sortValues.head or s.sortValues.head or foo.bar.whatever sortValues.head, things like that. So that's the idea of the varying parts. And then we give them names because we want to reuse them in the RHS. So here we say if you match such a thing, you want to replace it with the same expression that you matched here, dot and smallest, and n equal to the n to the constant number you matched here. So that's how this works. And this rule will in fact give us the speedup that we just saw earlier. But the problem is this rule is not exactly correct. It's correct only under certain preconditions, meaning some conditions that have to be true for the rewrite to be correct. So the precondition here is that the type of this called-on expression that we match is a Pandas series. Now, there are two important things to note here. First of all, this precondition is dynamic because it requires the type of the expression which we only know at runtime. Second of all, most of the complexity in Dias is in checking these preconditions. So let's just go and see what kind of complexity Dias has to deal with. So here's a complicated expression Dias has to deal with. So we have this function call expression, this call to test, that has multiple sub-expressions in it. So the first argument is a call to modx, which is, we assume is a function that modifies a variable x. And we also see this readx here, which is supposed to read from x. And this second argument matches our rule, because we have this expression here, foo.readx.sortValues.head. So this is an expression that is followed by sortValues head. The important thing here is that whatever we do, this needs to read the updated version of x. So the version that comes after this modification. The question is, how do we test that? We can't really check this whole expression, say, before here, before the call to test. Because then, in our precondition checking, we're going to be using an obsolete value of x. So what we need to do is we need to perform the check right here, right exactly here, right when this expression would originally be called. So what we need to do is we need to bind the result of this expression into a variable and then check the preconditions on this variable. But to do that, within such a sub-expression, we need a local binding. We can't do it through a normal variable assignment, say, in Python. We can't have a variable assignment inside a function call. But the problem is, Python doesn't have local bindings like OCaml does, for example. So we need to be a little bit innovative with that. And the way we dealt with that in the Dias implementation is we pass this expression as a function argument, which then gives us a local binding into the function Modin. And this function does the checks. The other important feature of Dias is that it can perform optimizations that cross library boundaries. Here we have some original code, and what the user wants to do is concatenate two series. So the way they do it, and this is relatively common, is they take the first series, they turn it into a list, they take the second series, they turn it into a list, then they concatenate these two lists, and then they turn the result back into a series. A much faster way to do that is to use the Pandas provided PD concat, which takes the two series, concatenates them, and we say ignore the index because that's what the original code effectively does by turning them into lists. Now the important thing here is the original code, because it goes in and out of the library boundaries of Pandas. Now we start executing the code. We access these two series. And when we do that, we are within the Pandas API. Pandas has view and control over what's happening. But by turning them into lists, we go out of the Pandas API. So Pandas doesn't have any control over that, because now the objects are just Python objects, not Pandas objects. So we do the concatenation in Python, and we turn the result back into the Pandas API. So we see here that we have two crossings of the Pandas library boundaries, one out of Pandas and one into Pandas. Such cases are very hard for Pandas implementations to deal with, not only for Pandas itself, but also any Pandas replacement. But this is something that DAS can easily deal with, because it's just a rewriter that views all of the user's code, and it can naturally understand it and control it and rewrite it. I'll finish this presentation with some experimental evaluations. Let's start with a setup. For this experimental setup, we use 10 randomly picked Kaggle notebooks. We use a commodity machine, so 32 gigs of RAM and just a standard CPU. And the reason we do that is because, as we said in the beginning, most of these EDA workloads run on single machines, and usually these machines are not powerful. So it's people's personal laptops or the virtual machines provided by Kaggle and Google Colab. And these virtual machines are not really that powerful. They're definitely less powerful than this. So now first compare DAS with Pandas, which forms the baseline. In this plot, on the x-axis, we have the 10 different notebooks, and on the y-axis, we have the relative speedup compared to Pandas. And of course, higher is better. Pretty important also is this 1.0 line, because if we're above this line, it means we have a speedup. If we're below this line, it means we have a slowdown. Now the highest speedup is significant. We have a 3.6x speedup of, again, whole notebook end to end. The biggest slowdown is not that significant. It's 0.97x, which again reinforces our belief that DAS doesn't really slow down in notebooks. Here we have per cell measurements. Sometimes folks care more about these. They care more about running a specific cell. On the x-axis, we have again the cells. On the y-axis, we have the relative speedup, again compared to Pandas. Here we can see much more important speedup. So the highest speedup here is 57x. Then we compared DAS with Modin, because it's the most popular Pandas alternative. So here on the x-axis, again, we have the 10 notebooks. On the y-axis, we have the relative speedup, again, based on Pandas, and we have 4 configurations. So we have DAS, we have Modin with 4 cores, Modin with 8 cores, and Modin with 12 cores. And what we can see here is that DAS is consistently faster than Modin. In fact, it's faster in 9 out of the 10 cases. And for these 9 cases, it's not just that DAS is faster than Modin, it's also that Modin is slower than the baseline Pandas. In fact, sometimes significantly slower. That said, you can see here that there is a notebook in which Modin is faster than both DAS and Pandas. And for this notebook, it actually scales as we increase the number of cores. The reason we see this speed up and the reason we see the scaling is because this notebook is dominated by an apply call, and Modin is able to parallelize that. Okay, so the last thing we're going to do here is we're going to try to get an estimate of DAS's heat rate across thousands of notebooks. Now, unfortunately, we will have to settle for an estimate, not an actual computation, because that would require running thousands of notebooks, since DAS is a dynamic technique. But it's very hard to run notebooks automatically, and that's such an experiment was infeasible. So what we do here is we test about 9,000 notebooks and 180,000 cells, and we perform a static analysis. So we consider it a hit when DAS matches the LHS. This is a good estimate because usually when DAS matches the LHS of a rule, almost always the preconditions pass, so the rule actually applies. And the results we get is that we hit in about 3.2% of the cells and about 27.1% of the notebooks. And these results we think are encouraging because they're very similar to the actual hit rate we got in the 10 notebooks we tested. So that was a presentation for DAS. The key takeaways are that DAS is the first lightweight solution for EDA workloads that use Pandas. It is automatic and correct, you just need to import it, and nevertheless, DAS can provide huge speedups. DAS is open source, you can download it here, and also you can find here the code for the experiments, both the experiments that you saw in this presentation and the experiments that you see in the paper. Thank you very much for watching. Please let me know what you think about DAS. by either shooting me an email or by posting your thoughts down in the comments. And finally, more information about DIAS is going to be in the video description. Thank you. Bye-bye.